You know, in the world of AI, everybody's looking for that edge, right? A way to build faster, smarter, more efficient models, especially when you're on the clock in something like a hackathon. So today, we're going to unpack a secret weapon that's not about more processing power, but more brain power. So let me just ask you this. How do you actually win an AI hackathon without a supercomputer? I mean, seriously, how do you compete, let alone win, when it feels like you need a whole server farm just to get off the ground? The biggest models need massive resources. But what if there was a way to punch way, way above your weight class? Look, let's be real. We are in the middle of a full-blown AI arms race. And for a while now, the thinking has been pretty simple. Bigger is better. More parameters, more data, more compute. But that just creates this huge barrier to entry. And you can see the scale of this problem right here. A standard vision transformer, a VIT-based model, is an absolute beast with 86 million parameters. But then look at a more data-efficient model, like a compact convolutional transformer. It gets competitive results with just 3.7 million. I mean, that's a huge difference. And here's the thing, right? This whole data-hungry paradigm, it basically locks the door on tons of brilliant people. We're talking students, indie developers, hackathon teams. Anyone without a massive budget is left at a huge disadvantage. But what if the whole blueprint we've been using for AI is, well, incomplete? So where do we find a better blueprint? Well, the answer, and this is the cool part, comes from the human brain. It turns out the basic building block of most AI is based on an understanding of our neurons from over 60 years ago. And trust me, neuroscience has come a long, long way since the 50s. This timeline really lays it all out. The perceptron, which is the foundation for our artificial neuron, was thought up way back in 1958. Jump to 2005, and scientists have this way deeper understanding of something called dendritic computation, which was pretty much ignored by AI until just recently. It's like we've been missing a key piece of the puzzle this whole time. So what is this missing piece? It's the dendrite. For decades, AI has pretty much treated neuron inputs like simple wires with weights on them. But in a real brain, dendrites are these active computing units. They process and transform information before it even gets to the main part of the cell. They're kind of like a neuron's own little mini brain. And wow, when you see them side by side, the difference is just stark. On the left, you've got your standard artificial neuron, a simple sum of inputs. And on the right, you've got the biological reality, this incredibly complex, branching tree that's doing all sorts of sophisticated math. It's so obvious we've been leaving a ton of computational power on the table. Okay, so the million-dollar question is, how do we actually turn this amazing biology into code? Well, researchers have been on it, and two main approaches have really started to stand out. So there are basically two main ways people are tackling this. First, a simple pre-processing step, and second, a more complex method for error correction. Let's start with a simple one. Okay, check out this experiment on sound localization. Researchers added a simple dendritic layer that did just one thing. It added a tiny little time delay to an input. And the result? This small, brain-inspired network could do the exact same job as a traditional network that was twice its size. That is a huge win for efficiency, just from one tiny brain-inspired tweak. But the really game-changing idea is something called perforated backpropagation. Okay, this is where things get really clever. Instead of just pre-processing the data, you add these dendrite nodes to a network you've already trained, and their one job, is to learn how to predict when the neuron they're attached to is about to mess up. Okay, so here's the magic trick. Normally, the whole network learns together from an error, but with this technique, you kind of perforate the learning process. The error signal gets sent sideways just to the dendrite. This lets that dendrite train for one job and one job only, spotting the patterns that make its neuron fail. It basically becomes this super specialized mistake corrector. All right, this science is amazing, but how does this help you win your next hackathon? Well, this is exactly where all that cool theory turns into a seriously powerful practical tool. So the team that came up with this has released an open source library that lets you plug these artificial dendrites into pretty much any PyTorch model. You're not building something new from the ground up. Nope. You're upgrading the models you already know and love. And get this, and this is the real kicker for anyone in a hackathon. You can get this up and running in your project in under an hour. We're not talking about a month-long research project here. This is a weekend hack that could give you an insane advantage. And hey, don't just take my word for it.
Evan Davis, who actually won first place at an AI optimization hackathon using this, said they got it working across a whole bunch of different BERT models in just 1 week. So yeah, this tool isn't just powerful on paper. It's a proven winner in a real-world, high-pressure situation, like, a hackathon.